Thanks, everybody. Give it up for VM Day, Cartesi, Fuel. So my name's Hans. I'm a developer at Risco Zero. We're a company that's trying to pioneer verifiable computing. What does that mean? Well, we have a virtual machine, hence VM Day, and we verify it with zero-knowledge proofs. Specifically, this virtual machine is built on the Risc instruction set architecture, and we utilize ZK Starks to prove that. We do that because the VM itself and the Risc instruction set is the circuit. This addresses the growing needs for privacy, as well as security and computational processes in a, in theory, decentralized way. It's ideal for applications requiring data integrity, confidentiality, and of course, that's useful in blockchains, finance, and a number of growing fields. So, how do we do this? Well, like I said, it's a zero-knowledge virtual machine. It emulates the Risc instruction set. Risc, if you're not aware, is an open source instruction set, recently developed. It's available on consumer hardware in a growing fashion. It's a reduced instruction set. So typically, CPUs are something like x86. These are just really complicated instruction sets. They have quite a few instructions. Risc greatly reduces that and allows us to easily implement and constrain the system for zero-knowledge proving. We support languages like Rust. In fact, that's a first-class citizen. It's written mostly in Rust. But in theory, this should work with any compiled language that can be compiled to the Risc architecture. There's a growing demand for Risc and we hope to continue to see it grow. And we likely will, especially with the way chips work. Anyway, so the core of Risc and Risco Zero, zero-knowledge proofs. What are they? If you haven't heard, well, they're a way to prove data without necessarily revealing that data. What does this mean? Zero-knowledge proofs can validate computations without revealing the data or virtual machine state. We use ZK Starks to provide scalable, transparent, cryptographic proofs. Our design ensures that security is utmost, it's very important, and it allows us to ensure that the validation and integrity of processes carried out within the virtual machine are reproducible and verifiable. It's ideal for applications requiring integrity, so hence blockchains. It's easily integrated and verifiable with our Stark to Snark, basically minifying the zero-knowledge proof with our Banzai proving surface, which is just a bunch of GPUs. So how are we doing this, and how does it affect you? Well, our hope is to streamline this sort of execution. You write familiar code. You don't have to learn a specific DSL. You probably already want to learn Rust if you don't know it. And that's how we do it. There's various methods that go into maintaining the integrity of this. We use a couple of hashing methods to make sure nothing within the pipeline is actually modifiable without causing some sort of collision with the hashing. And so here's an overview. Basically, you write some code in the guest, which is the virtual machine. That's compiled to an ELF binary, put in an executor. Inside of this box is where this execution happens. This middle area represents an execution trace. In other words, what actually happens on the processor, where memory is written to, et cetera. That is proven, and you get back a receipt. So this ensures trust. It ensures computational correctness and integrity. Integrity seems to be a power word today. Verification process, confirms the integrity and correctness of that execution. It's essential for maintaining trust in the system. How is this useful? Well, it's shaping the future of secure computing. It opens a new era. It merges advanced cryptography with open and flexible standards, that is Risc-V. And it addresses the critical need for security and verifiability, as well as privacy in the ZK setting and context, which is incredibly useful for blockchains and finance and healthcare and any other sort of data-sensitive sector. So what are some of the challenges we have ahead? First, hardware requirements. Proving things is demanding. We have Bonsai. That's our proving service. It's a bunch of GPUs. It's not exactly cheap, but it's worth it. Virtual machine performance. Right now, the VM, the ZK VM, runs in the megahertz range. We'd like to see that in the gigahertz range. We're also constrained by memory. It's nowhere near as performant as your laptop or possibly even your phone, but that's improving day by day. Risc-V adoption. Well, Risc-V is an interesting thing. It's certainly being more adopted. It will take some time, though. Language adoption, package support, and developer tooling. Basically, learning Rust, learning other compiled languages, probably worth the effort. But hey, decentralization hasn't been a priority for Risco Zero, but it's important. And of course, getting the word out. It's up to us to spread the word that these things are possible. You can use these snarks on-chain for verifying things on-chain. So it opens up a whole world of possibilities. Anyway, that's our QR code. Scan it if you'd like to have some more info. We look forward to your questions. Thank you.
Does anybody have any questions? I can bring a mic to you.
What are some of the use cases or applications you're currently seeing an interest from for using Risc?
Yeah, so the applications are pretty vast. I mean, you write normal code. You're not thinking in circuit languages. You're not thinking in special DSLs. You're not really even writing code that you would think needs to be in a ZK proof. You just write normal code. And that's pretty amazing. Because you can basically co-process all of that code off-chain and then post that back on-chain and verify that on-chain using Groth 16 verifier with the start-to-snark pipeline I mentioned. So it allows you to remove computation from on-chain, which is, of course, expensive and gas-intensive, and still have that in a verifiable way that anybody can verify. So if your program runs in, let's just say it's a really complicated program, you don't necessarily want people to have to rerun that either. So they can just verify the proof, sublinear time, and it's pretty useful, especially when you want to put stuff on-chain. We have a couple of applications that we've actually developed in the last couple of days that demonstrate this. You can check it out on our website or Twitter. And one of them is Bonsai Pay, and it's using the Bonsai proving service to generate proofs that are verified on-chain so that way you can send crypto to your email address effectively. It's pretty useful. It unlocks a whole world of possibilities. Anyway, next.
Cool, thank you. One question, if I want to run a Bonsai prover myself, how much GPU do I need?
Well,
Or how little do I need, maybe?
You can run it off of your probably consumer-grade laptop. There's a time constraint here, though. People don't like having to wait hours. So the Bonsai proving service runs on anywhere from 50 to 100 GPUs. I don't remember the exact GPU model, but that usually reduces a few billion cycles down to a couple of minutes.
Okay, we have time for one last quick question.
I'll make it quick. So compared to a DSL, if you write your circuit in a DSL, intuitively, I would think that it's probably more optimized.
Yes.
How do you see that for the future of Risc Zero? Do you see that? Because I kind of see that as if you're writing something in production, go write it in a DSL. If you want to do something fast, easy, write it in Risc Zero. How do you, any comments on that?
Sure, yeah. So there's definitely a performance difference, and there likely always will be, but we're focused on general computation. Having a DSL, well, it might be a fully featured language. It's often difficult, and you need specialized people, and you need specialized talent in order to do so. This removes that. I'd say it's sort of analogous to like ASICs versus CPUs. What won in the end? CPUs.
Okay.
Yeah.
I think we have to wrap it up. Thank you so much.
Sure thing.